Alright, so today's lecture in Electronics 110 is about mesh currents with independent sources. So this is the first lecture where we're going to be talking about actually solving more complex circuits without using equivalent resistance. So this is setting the groundwork for solving things with capacitors and inductors and more interesting components that behave in different ways. So mesh currents is one of two ways we're going to be solving circuits. The other one we'll talk about in a couple videos. But they both rely, or each rely on one half of Kirchhoff's laws. This one relies on Kirchhoff's voltage law. Remember that Kirchhoff's voltage law states that the sum of voltages in a loop is zero. And we're going to define what a loop is, and we're going to finally understand what that means in its entirety. Now, independent sources means that every source we're going to be talking about is independent of anything else. That'll make more sense in the next video where we talk about mesh currents with dependent sources, where you'll be able to see what a dependent source means and compare it to an independent source and learn what the independent source means. Okay, so let's start with the most basic circuit we have that doesn't break any rules, namely this circuit, where we have a voltage supply, we'll call V sub S, and a resistor R. Now, the goal of this is solving this circuit, solving everything about the circuit. Voltage drop across the resistor, the current through the resistor, the current delivered by the voltage supply, the power delivered and consumed by each component. We're going to be solving all of that without equivalent resistance. Now, I say that you can solve these with equivalent resistance. In fact, solving these with equivalent resistance, or using equivalent resistance, does become a big help when these circuits become very large and unwieldy. However, for these, we're going to do it without anything. Again, trying to lay the groundwork for later, more complex circuits. Oh, scroll down a bit too far. So, solving these without equivalent resistance. No cheating. Do the work. Now, the goal is to solve for the current loop. So there's a loop here. You can see it's an entirely closed circuit. There's a connection to the beginning of the circuit and a connection to ground, or the implied ground, which I'll draw on right now. So what we want to do is solve for this current. And once we solve for the current, we can solve for the voltage drop across the resistor, the current supplied by the supply, the power delivered by the supply, and the power delivered by, or the power consumed rather, by the resistor. Once we do all that, well, you know everything. So this is one loop. When you have multiple loops, which you'll see later, you'll have a mesh. And so, now, important thing to note about this current. Current, remember, is, in terms of this, it has direction. It has a vector, if you will. The arrow indicates the direction of the loop. So this comes out, up, down, and back around. That's going to be important to recognize later. Everything has a direction. So let's take this circuit. I will just copy it and paste it. So Control C, V, there we go. So let's put this down here. Okay, so how do we solve this? Well, remember that sum of the voltages in a loop must be zero. We have a loop here, so the sum of the voltages about it must be zero. So we know that the voltage supply supplies voltage, so that's going to be here. Now, the resistor's job is to consume voltage. Well, consume voltage in a manner of speaking. Now, you'll see some people denote in their circuits, especially in early lectures, if you go through a formal course like this. A battery has, or a supply has, a positive and negative side. A resistor has the same thing. It's got a positive and a negative. Now, resistor doesn't actually have a positive and a negative, but it's used to show that as current comes around, if current goes from negative to positive, it's a positive. This has an implied positive sign. However, if it goes from positive to negative, there's an implied negative sign. So this is minus IR. So this is the voltage supplied minus the voltage consumed by the resistor. Remember the voltage equation for resistor IR. Now, we can rewrite this as Vs equals IR. And this is what I'm going to consider standard form for these problems. So it's a good way to remember that, or it's a good thing to remember. The left-hand side, the LHS, is the supply. And the right-hand side, the RHS, is the demand, we'll call it. So the supply and demand, the supply and the consumption, the give and the take, however you want to call it. Left-hand side is what's supplied, and the right-hand side is what's demanded, it's what's taken. Now, obviously, direction is going to matter on both sides, depending on the situation, which we'll talk about a little later when we get to some weirder problems. But before that, let's just go ahead and solve this so you can just, friendly reminder as to how this all works. So Vs has to equal IR, and we're trying to solve for I. Vs here we'll call 1, and we'll call R here 1 ohm. So 1 equals 1 times I, so I equals 1 amp. So the current through the system, the current through this loop is 1 amp. That means everything that touches, or everything that is on this loop, has 1 amp flowing through it. So if we look at, the current delivered by the voltage source is 1 amp, and the power delivered, that's a D, not a P, power delivered by the voltage source is 1 watt. Useful to remember all of the equations. V equals IR, power is IV is IR squared. No, forget that one. Just use IV. IV is going to get you through all of this. So power is 1 watt, IV. The current through the resistor is 1 amp because it's on the loop. The voltage drop across the resistor is 1 volt, IR, and the power across the resistor is also 1 watt. And you'll start to notice some things as we solve these, like the voltage across the voltage summed in a loop is 0, we already see that, and the power summed across all the components must equal the power delivered. You'll see that. Now, I say everything on the loop is only every component on the loop just behaves according to this loop. You'll see later when we start to mesh the loops, when we start to get mesh currents, that's not the case. So there are some other things you have to consider. But until then, let's go ahead and solve another circuit. Let's start to get a little more complicated. We'll start with a series circuit. Now again, this is a circuit you can solve with equivalent resistance, but we're not doing that. So we have a resistor and another resistor in series, and we have a current loop, and we'll call this current I. This is R1, this is R2, and this is Vs. So this is 1 volt, this is 1 ohm, and this is 1 ohm. So let's set up. Remember, the right-hand side is the voltage supply, so Vs, and then the right-hand side is the voltage consumed. So this is going to be the voltage consumed by this, which is I, R1, plus the voltage consumed here, which is I, R2. Replace everything, we get I times 1 plus I times 1. So 1 equals 2I, and I is just 1/2 amp. And so there you have it. Now we know what the current through the loop is, so we can go back and figure. Darn it! Stop it. Let's go back. There we go. So we can go back and solve for everything. Power, or before we get to power, current delivered by the voltage source is 1/2 amp. The power delivered by the voltage source is 500. I'm not going to do it that way. 1/2 watt. The current through R1 is 1/2 amp. The current through R2 is 1/2 amp. The voltage drop across R1 is, remember, it's IR, so this is 1/2 volt, and the same is true for R2, which is also 1/2 volt. and then power through R1. Power is I times V, so 1/2 times 1/2 is 1/4 watt. And again, the same is true for here. This is 1/4 watt. Okay, darn it. So here we can see some of the things I talked about and some of the things you should remember from previous lectures. In a series circuit, the current through all of the components on the loop is the same, so current is all the same. The sum of the voltages should be same, so the voltage supplied, 1 volt, should be the sum of these voltages. It is in fact 1. And the power consumed should be the same as the power delivered. 1/2 watt is the same thing as 2 times 1/4 watt, 1/2 watt. So everything holds. Everything, I guess we did okay. So let's move on to a parallel circuit. Again, another circuit you can solve using equivalent resistance, but again, we're not going to. Now this is the first circuit where we're going to see an actual mesh current. Because what you should see, Vs, R1, and R2, what you should see is now that there are 2 loops. We're going to call this one I1. We're going to call this one I2. And we're going to, well, before we get to that. Now, there are a few things you should notice. Remember, current has a direction. This is important. Now, this is where you have to sort of make an assumption. Because I know this circuit, I drew up this circuit, I know what it does, I know that current is going to go through, or current is going to come out of the supply, go down and around. So this defines I1. I also know, just from experience and looking at other circuits, that current is going to come out from this node, come through in this direction. So in the same direction as I1. Now, if you make a wrong assumption, if your assumption is, say, backwards, it just means that your current is going to be negative for that loop. It just means that your assumption was backwards. Nothing wrong, it's just you don't actually get a different number, you just get the opposite number. So everything still works. So, let's say, come on, pen. V1, or not V1, Vs is 1 volt. R1 is 1 ohm, or not 1 ohm, is 2, come on, pen. 2 ohms, there we go. And R2 is also 2 ohms. Okay. So now that we have 2 loops, we have to draw 2 equations. So one equation we will call loop 1, and another equation we'll call loop 2. Now, for loop 1, we have the voltage supply equals, now this is where, just because the component is on, well, the component is on a loop, one loop, it's on loop 1, I1, but it's also on another loop. It's also being held in some way by, or it's being controlled in some way by I2, loop 2. So we have to write something which signifies that. And the way we do that is we say I1 minus I2 R1. This is, that's a terrible error, this is the mesh. So this represents 2 circuits, or 2 loops interacting with one component, the mesh of 2 currents. So it's the mesh current analysis, and so we get the name. Now, why is it negative? Well, let's start with this. Loop 1, meaning we're talking about current loop 1, is the first number, so everything is done with respect to that. Now, because the 2 loops are moving in opposite directions to each other, loop 1 is coming down R1 and loop 2 is going up R1, the current through this is going to be in some way diminished. It's going to be less than either of these 2. Or it's going to be the reduction of either of these 2. So, moving in opposite directions, one minus the other. Moving in the same direction, they add on to each other. So, you could imagine that if I2 was moving down, the current going through R1 would be added in some way. And we'll see that in a the next example. So that is the mesh. This is how you draw the mesh. It's the interaction between the loop current we're talking about, I1 in this case, and another current, I2. So R1 is the only one that interacts with loop 1, so we'll move on to this one. So here, Vs equals, we have to deal with this guy again because R1 is also interacting with loop 2, but we're on loop 2, so we deal with it like this, I2 minus I1, R1, because now we're in loop 2, so we deal with respect to I2 minus I1, the minus indicating that the two loops move in opposite directions to each other, plus I2 R2, which is the interaction of loop 2 with R2. Okay, so let's fill some numbers in. Vs is 1 equals, and R2 is 2, so this is 2I1 minus 2I2. Here, there is no voltage supply in this loop. There's no battery, there's no voltage supply, there's no anything supply, so this is just 0. Equals, R1 again is 2, so this is 2I2 minus 2I1 plus 2I2, because R2 is 2, and if we sum that together, 0 equals negative 2I1 plus 4I2. Now, we could solve this using substitution, plugging it all in. I prefer to just take this and plug it into a matrix. So if you've never used a matrix, it's a great thing. It really saves time solving for linear systems of equations, because this is a system of equations and it is linear. There's no square in it anywhere. So this is how you draw a matrix. If you have no idea what I'm doing, I'll explain the practical bit of it in just a second. But basically what you want to do is line up all the constants. So everything here is I1, everything here is I2, and over here is the constants. Whenever you're trying to create a matrix or arrange things in a matrix, you want to ensure that all of the variables and their coefficients are on one side, and all of the constants are on the other side. Then what you can do is plug it into something which will solve a matrix, and perform an RREF, a reduced row echelon form. You can do that on a graphing calculator. I know TI-84 will do it. I'm going to do it in Wolfram Alpha because that just requires an internet connection. So to plug it in, I'm going to use curly brackets, and Wolfram Alpha understands this row-wise, not column-wise. So you fill in a row, and then you move on to the next row. So this row is 2, negative 2, and then the constant 1. And then in this row, it's negative 2, 4, 0. And it should interpret that as a matrix, which it does. And actually, if I ask for REF of that, row reduce, we get this. Can I? No, I can't. So I'll just write it down because I've got it written down here. So if you reduce row echelon this, you get something that looks like this: 1, 0, 0, 1, 1, I2 equals 1, 1 half. Okay, so what this means is 1 times I1 plus 0 times I2 is 1, and 0 times I1 plus 1 times I2 is 1 half. So if you just write that out, I1 is 1 amp, and I2 is 1 half amp. So just look at that again. It's reduced row echelon, and then column-wise 2, negative 2, 1, negative 2, 4, 0. So if you don't know how to use matrices, you can solve this by hand, but it does get a little bit unwieldy for a lot larger matrices. So using something like Wolfram Alpha to solve the matrix saves you a lot of time. MATLAB will do this too if you have access to MATLAB. Maple will probably do it too. But this is the result, which I plugged in. So again, you can solve this by hand. Matrices make it a lot better. Okay, so getting back to what I was doing. So let's take this answer. Actually, let's take this entire thing, copy it, move to the next page, boop, go back and copy this, bring that here. Okay. So let's answer some of these questions. The current supplied by Vs is just I1, so this is just 1 amp. The power supplied by Vs is IV, so this is just 1 watt. Okay, so current across R1, we'll get back to that. Current across R2 is just I2, so this is just 1/2 amp. The voltage across R2 is 1/2 volt. No, it's 1/2 times 2, my bad, so this is just 1 volt. And the power across R2 is IV, so it's just 1 watt. Okay, now we come back to the current across R1. R1 interacts with both I1 and I2, so we have to figure out some way to write that. We already have that. We have this mesh here, I1 minus I2 or I2 minus I1. Which one do you pick? Well, remember what I said. If you get a negative answer, it just means what you chose was backwards. So I1 minus I2 gives 1/2 amp, and I2 minus I1 gives negative 1/2 amp. The negative means you were just backwards, so you flip the sign of these two around, and you just get this. So it's just I1 minus I2, which is 1/2 amp. And then from that, you can solve for everything else. Voltage across R1 is 1 volt, and the power delivered is... oh, this shouldn't be that. This should be 1/2 watt. What am I doing? 1/2 watt, 1/2 watt. I made a mistake in my notes. I didn't do the math. That was silly of me. Okay. So remember, negative just means you need to flip the sign around. It just means the direction you picked is the opposite of the direction things are actually moving. So if I'd picked I2 minus I1, it means that the current is actually moving up R1, as opposed to I1 minus I2, where current is moving down R1. Because I1 would be greater, it would overpower I2, and this direction would follow. If I2 is bigger than I1, this direction would follow through and it would push up. Okay, so this is mesh currents. Let's do another mesh current. This one you can't solve with equivalent resistance. So we're finally at that. So we're going to have not one, but 2 voltage sources in this problem, or in this example. Up. There we go. So this is we'll just call this V1, this V2, R1, R2, and R3. And this is current 1, and this is current 2. Now, before I go about filling in the numbers for this problem, note the directions I picked. I'm generally assuming the current is going to flow based upon the voltage. So the voltage is going to come up, down, and around, up, down, and around. So the current through here is going to be summed in some way. Obviously, I could be wrong about this assumption. That's going to change depending on the values for V1, and V2, and some of the other values, R1, R2, and R3. So I pick one that makes sense in my head. And again, if I get it wrong, it just means that the signs are going to be reversed, and I'm not going to get any different numbers. So again, it's just the assumption I make. So with that, let's give some values. We'll make V1 equal to V2 equal to 1 volt, and R1 equal to R2 equal to R3, and we'll just make them 1 ohm. Okay, so, darn it. So again, we have 2 loops, so we need 2 equations. So loop 1 and loop 2. So V1 has to equal I1 R1 plus, remember we've got a mesh here, but now the meshes are moving in the same direction. They're both moving down R3. So I just add them. So I1 plus I2 R3. And for loop 2, V2 has to equal I2 times R2. And then we have to deal with the mesh again. But we're in loop 2, so we deal with I2 first, but it really doesn't matter since it's just I2 plus I1 times R3. And then we plug in some numbers, so 1 equals I1 times 1 plus I1 plus I2 times 1, and 1 equals I2 times 1 plus, what is that? I2 plus I1 times 1. So 1 equals, what do we have here? It's written right here. 2I1 plus I2, and 1 here equals 2I2 plus I1. So now we just have to solve this, and again we can use a matrix to do this, and indeed we are going to in fact use a matrix to do this. So I have 2, 1, 1, 2. So this is the coefficient from loop 1. This is loop 1. The coefficient of I1, coefficient of I2. And this is loop 2, coefficient of I1, coefficient of I2. Times I1, I2 equals the constants. In both cases is just 1. So this is another reason I rewrote it Vs equals IR. Because Vs is generally the constant. So it makes it easier to just plug it into matrix form. So we go back to Wolfram Alpha and just change some of these numbers. That stays as 2, this becomes 1, that stays as 1. This, however, is now 1, this is 2, and that becomes 1. So I hit enter, Wolfram Alpha comes back, and it gives me the reduced row echelon form, telling me that 1, 0, 0, 1 times I1, I2 equals 1/3, 1/3. Meaning that I1 is 1/3 amp, and I2 is also 1/3 amp. And again, no negatives, meaning that my assumption was right about the direction of the loops. So now we just have to solve for everything, which I leave as an exercise to you because that's pretty much just busy work and you know how to solve it. It's just, again, V equals IR, and power is IV, so it's straightforward. And you know what the mesh is for I3. It's just the sum of these two, so again, fairly straightforward. So there is one more thing we need to talk about, and that is the concept of, well, actually, before we get to that, one last thing we need to talk about, I'm going to talk about direction, because I brought this up at the beginning, and it's an important thing to bring up, because you need to understand how direction of current and direction of supplies impacts things. So let's just take this circuit. Let's just take this circuit, paste it down here. But I'm just going to change one thing. I'm going to take this and invert it. What did I do? Well, now I've reversed the current direction of I2. Remember I drew the positive and minus signs on the battery. Current's coming out from the positive and going around into, well, I've changed the direction of loop 2. So if I keep all of the magnitudes for V1, V2, R1, R2, and R3 the same, you should see that the mesh current across R3 is 0, because the magnitudes of the loop currents, or the mesh currents, are now in equal but opposite directions, so they just sum to be 0. So it's an important thing to also make note of the directions of the supplies. Don't just assume that they're all going to move in the same direction. Make sure you look at which direction the supplies point. Draw little plus and minus signs if you need to. Anything to help you get the right answer. Now, another weird case we should consider is this one. And I'm drawing it on a diagonal. So what we have here are two supplies. And I'm just going to draw on their values here. 1 ohm, 1 volt, and 1 volt. So what's going to go on here? Well, if I call this one I1 and this one I2, these two things have the same magnitude. So if you have a feel for things, plus minus, you should see that the current I1 is going to be 0. However, the current I2 is just going to be 1 amp. Why is that? If we examine loop 1, we have, we'll call this V1, and we'll call this one V2. We have V1 minus V2 equals I1, I1, R1. Call this R1, R2. Why the minus sign? Well, remember what I said about the plus minus thing. The loop is coming out from V1, going across R1, then it's running into V2, and it's going from plus to minus, so I have to invert the sign of the supply. And when you do this, these two cancel out, and you just get 0 on the side equals I1, R1. So obviously I1 has to be 0. And R2 doesn't interact with I1 in any way. It only interacts with I2 and V2. So it has its own answer. So these are things you have to pay attention to. And if you do a lot of these problems, you start to get a feel for, oh yeah, these batteries are in the same direction, or they're in opposite directions, and that has such an impact. So again, little plus and minus signs go a long way. Okay, so these are the weird well, they're not the weird cases. They're cases where direction matters, and you should always pay attention to the direction of things. Because I've gotten questions where the direction of things matters, and I've kind of overlooked that. And I've gotten it wrong. So I'm helping you not make that mistake. Okay, the last thing we have to talk about is a source we haven't talked about before, and that is the current source. I could probably write that a little better. Current source. Underline. Okay. So a current source we denote like this, or at least I denote like this, and because I'm teaching, you're all going to denote it like this. The arrow indicates direction, and it supplies a current. So, and it has a couple properties. So if we were to take a current source and connect it to a resistor, and this is a 1 amp supply, and this is a 1 ohm resistance, the voltage across the resistor is 1 volt, IR. So the current source doesn't supply, or it has an infinite supply of voltage. It just depends on how much resistance it encounters. Same way a voltage source has an infinite current supply, it just depends on what it encounters. So another interesting property is, not interesting properties, a property you should know, is that when I connect it in series with a battery, or a voltage source, not a battery, this is, say, 2 volts, and this is 1 amp. The voltage drop across this resistor is still 1 volt. So the thing you should notice is that the loop current, because we're talking about loop currents and mesh currents, the loop current is the supply current. So this is the supply current. So the loop through the loop current is 1 amp, and the loop current here is 1 amp. Doesn't matter what resistance the voltage supply encounters, it's all going to be regulated to 1 amp. No more, no less. Now, in series, this is the case. There is a case we will talk about later, which is this, in which there are other things we have to consider. And this is, again, we'll talk about this in a couple lectures. We're not going to get to it right now. So let's do a quick example with current sources. I think I still have this in my clipboard. I do. So I'm just going to make a change here. This is not going to be a voltage source anymore. This is now going to be a current source. And this is going to be 1 amp. So that's 1 amp. V2 is still 1 volt, and R1 still equals R2, still equals R3, equals 1 ohm. Yeah, oh no, this is 2 volts. I made a note in my notes to make that 2 volts. Okay. So if we solve for this, again, we've got 2 loops, so we need 2 equations. Loop 1 and loop 2. Now, loop 1, we already know because we made note of this behavior up here. The loop current is set by the current supply, barring this example. So loop 1 is just 1 amp. So I1 equals 1 amp. Congrats, you've solved it already. Loop 2, V2 equals I1 plus I2. Again, direction of the currents moving in the same direction, so it's just plus, except I did that backwards. This should be I2 plus I1, because we're dealing with respect to loop 2, times R3 plus I2 R2. So substituting everything in, 2 equals 1, or I2 plus 1 times 1 plus 1 times I2. So 2 equals I2 plus, actually this is 2I2 plus 1. So 2I2 equals 1, and I2 is just 1/2 amp. And there we go. So we solved I2 and I1. Now if we go back and solve some things, we see this time we don't deal with current supplied by the current source because it's already supplying current. So the voltage by the current supply, which we'll denote IS. I guess I should write that up here as well. This is IS. And in this case, it's the sum of the voltages in that loop, which we'll have to get back to later, and power delivered by the current supply. Again, we'll get to that later. The current across R1 is just... Oh, where's my... There it is. Stop it. Stop scrolling. Current across R1 is just I1, so this is just 1 amp. Voltage across R1 is just 1 volt. So the power across R1 is 1 watt. Current across R2 is just current 2, loop 2, so that's just 1/2 amp. The voltage across R2 is V equals IR. So I is, so yeah, it's just 1/2 volt. And the power across R2 is 1/4 watt. Current across R3 is the mesh between I1 and I2. So this is just 1 1/2 amp. So the voltage across R3, not R2, is 1.5 volts, and the power across R3 is IR. 3 halves times 3 halves is 9/4. I'm sure that reduces down to something. Anyway, so not volts, watts. There we go. Okay, so voltage delivered, voltage delivered by the current supply is the sum of all the voltages in loop 1. So that's the sum of voltages across R1, 1 volt, and R3. So this is 2.5 volts. And then the power delivered is the sum of those two. So this is 1 watt plus 9/4 watts, which is 13/4 watts. And so there you have it. I guess we could look at current delivered by V2 is just I2, which is 1/2 amp, and then the power delivered by V2 is IV, which is just 1 watt. Okay, so there you have it. That is everything. So this is mesh current analysis using with only independent sources. Next time we'll talk about mesh currents with dependent sources. Things get a little more tricky. We have to do a little more math. If you aren't familiar with matrices, after this video, I suggest watching or looking how to do matrix math or getting a better understanding of how to do matrix math, because it's going to be a much bigger help in the next video when we have to deal with many more variables. So until then, thanks for watching.